You're accelerating toward the speed of light, and at 99.9% light speed, something impossible happens. The energy needed to push you even slightly faster becomes 22 times greater than what you needed at the beginning. At 99.99%, you need 71 times more energy than when you started. At 99.999%, over 224 times more. And you haven't even reached light speed yet. In fact, you never will, because the final 0.01% would require literally infinite energy. But what happens in those last moments before you hit that impossible wall? The answer will change how you think about reality itself. Let's start with what light speed actually is. Light travels at 186,182 miles per second in a vacuum. That's fast enough to circle Earth's equator 7.5 times in 1 second. But here's what most people miss. Light speed isn't really about light. It's the speed limit of the universe itself. Information, energy, causality, nothing can travel faster than this cosmic speed limit. Think of it like this. Imagine the universe as a giant computer running reality. Light speed is the processor speed, the fastest rate at which any information can move from one place to another. When Einstein discovered this in 1905, he realized something profound. This speed limit isn't just a suggestion, it's built into the fabric of space and time itself. Now, why can't you reach light speed? It comes down to mass. Every object with mass, including you, has what physicists call rest mass. That's how much you weigh when you're sitting still. But here's where it gets weird. As you speed up, the energy required to accelerate you further increases dramatically. Here's what's actually happening. Every bit of energy your engine pumps into accelerating you doesn't just make you go faster, it also gets stored in you as increased resistance to further acceleration. It's like the energy is making you effectively heavier and harder to push. The faster you go, the more this resistance builds up, making each additional push require exponentially more energy. Think of it like trying to push a shopping cart that gets heavier the faster you push it. At first it's easy, but as you speed up, the cart becomes harder and harder to accelerate. Eventually, you'd need infinite strength to push it any faster. That's exactly what happens as you approach light speed. The energy needed grows without limit, so you'd need more energy than exists in the entire universe to go any faster. Picture this. You're in a spacecraft with the most powerful engine imaginable, one that can somehow keep accelerating you no matter how much energy it takes. At low speeds, and say 10% of light speed, things seem almost normal. You're traveling at about 88,600 miles per second, which is incredibly fast, but the weird effects are barely noticeable. For every 99.5 seconds you experience, 100 seconds pass on Earth. The difference is tiny. Push toward 50% light speed and reality starts shifting. Time becomes noticeably stretched. For every 52 minutes you experience, a full hour passes on Earth. If you could look back at Earth, you'd see everything moving slightly faster than normal. The energy your engine needs? It's already increased by 15%. Now here's where things get wild. At 90% light speed, the universe seems to be playing by completely different rules. The energy requirements have more than doubled. Time dilation becomes dramatic. For every 26 minutes you experience, an hour passes on Earth. If you left Earth and traveled for what feels like 1 year to you, over 2 years would have passed back home. But 99% light speed? That's where physics gets genuinely bizarre. The energy needed to accelerate you even a tiny bit more becomes astronomical. Time crawls from Earth's perspective. For every 3 minutes you experience, an hour passes back home. At 99.9% light speed, your engine is working 22 times harder than when you started, just to squeeze out tiny increases in speed. Time dilation is so extreme that for every year on Earth, you experience only about 5 days. But the numbers get even more extreme. You're still not at light speed. You're not even close to being close. At 99.99% light speed, the energy requirements have increased 71-fold compared to the beginning. For every day you experience, about 2 weeks pass on Earth. The energy needed to push you that final 0.01% toward light speed, it would take more energy than exists in multiple galaxies. Here's the crucial point. It's not that we haven't built engines powerful enough. The universe itself prevents you from reaching light speed. As you get closer and closer, the energy required grows without limit. You'd need more energy than exists in the entire universe. It's not a technological limitation. It's a fundamental law of physics. But here's where the story gets even stranger, because there are things that actually do travel at light speed, and understanding them reveals just how weird this cosmic speed limit really is. Photons, particles of light, travel at exactly light speed. But here's the key. They have zero rest mass. Because they have no mass, they don't face the energy barrier that stops you from reaching light speed. Think of it this way. If you have no mass, there's no shopping cart to push. Photons can only travel at light speed. They can never slow down or speed up. This creates something that sounds impossible. At light speed, time dilation becomes complete. Time stops entirely. So a photon emitted from a star 1,000 light-years away doesn't experience any time between leaving that star and hitting your eye. From our perspective, it's a 1,000-year journey. From the photon's perspective, the trip is instantaneous. Now here's where things get really complicated. While nothing can travel faster than light in a vacuum, light itself can be slowed down. In water, light travels at about 75% of its vacuum speed. In diamond, it slows to about 40%. This creates some bizarre possibilities. In nuclear reactors, something called Cherenkov radiation occurs. Electrons moving through water can actually travel faster than light travels in water. When this happens, you get a shockwave of light, a kind of light boom similar to a sonic boom. The result is that eerie blue glow you see in reactor pools. But even this doesn't violate Einstein's rules because the electrons still aren't exceeding light speed in a vacuum. It's like the difference between running faster than the speed of sound underwater versus running faster than the speed of sound in air. The medium matters. There's another complication that blows people's minds: quantum entanglement. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. This seems to violate the light speed limit, but it doesn't actually allow you to send information faster than light. The correlation is instant, but it's random. You can't use it to send a message. And here's perhaps the strangest complication of all. Space itself can expand faster than light. The most distant galaxies are moving away from us faster than light speed, not because they're moving through space that fast, but because space itself is expanding between us and them. It's like being on a treadmill that's speeding up faster than you can run. So why does this matter to you beyond just being a fascinating piece of physics? Understanding the approach to light speed reveals something profound about the nature of reality itself. First, it explains why interstellar travel is so challenging. Even if we could build spacecraft that approach light speed, the energy requirements become prohibitive. To accelerate a single person to 99.9% light speed would require more energy than the entire United States produces in several years. And that's just to get close, not even to reach light speed itself. But time dilation offers a strange kind of hope. If you could somehow survive the acceleration and travel at 99.9% light speed to a star 100 light-years away, the trip would take about 100 years from Earth's perspective. But for you, it would feel like only about 4.5 years. You could potentially travel to distant stars within a human lifetime. Your lifetime, even though centuries would pass on Earth. This has profound implications for how we think about space exploration. The traditional science fiction idea of faster-than-light travel might be impossible, but near-light-speed travel could allow humans to explore the galaxy, albeit at the cost of being forever separated from the Earth they left behind. The light speed limit also explains why the universe looks the way it does. When you look at stars, you're seeing them as they were years ago because that's how long their light took to reach you. The farther you look, the further back in time you see. The most distant galaxies we observe are showing us what the universe looked like over 13 billion years ago, when it was just a few 100 million years old. This means that if aliens exist on a planet 100 light-years away and they're looking at Earth right now, they're seeing Earth as it was in 1924. They're watching the Roaring Twenties, completely unaware of everything that's happened since. If they tried to send us a message today, we wouldn't receive it until 2124. Understanding these limits also helps us appreciate just how special our local cosmic neighborhood is. The speed of light creates a kind of cosmic loneliness. We're fundamentally isolated from most of the universe by the sheer time it takes for information to travel between stars. So here's what happens right before you reach light speed. You don't. The universe's laws make it impossible, not because we lack the technology, but because approaching light speed requires infinite energy. It's not a wall you hit, it's an asymptote you approach forever, getting closer and closer but never arriving. Every fraction of a percent closer to light speed demands exponentially more energy, until that final push would require more energy than exists in the observable universe. The cosmic speed limit isn't just fast, it's unreachable, making light speed not just the ultimate speed, but the ultimate impossibility for anything with mass. And in that impossibility lies one of the most beautiful truths about our universe. Some limits aren't meant to be broken, they're meant to define the very structure of reality itself.